This is a question from 2014 on the SS02 paper, and it's a Poisson distribution question. With a question like this, again, there's lots of information here, and it's become more common for Poisson questions in SS02 and binomial questions in S1b to include information from more than one distribution, as is the case here. This question is to do with rock samples and the emission of particles. We've got alpha particle, beta particles and gamma rays from the rock. What I've done to start this question, I've pre-planned some of the response, is I've actually taken the information from the question here, and again, as I've said before, I would really suggest underlining, or boxing, underlining and glancing back at the question, but I've taken the information down to the bottom of the page here, and the alpha particles are emitted and follow a Poisson distribution with mean 3.4, the beta with 2.6, and the gamma rays follow a Poisson distribution with a mean of 4. The first question asks us to find the probability that during a particular second fewer than 4 alpha particles are detected. Now this is for a second. The information in the question is actually given per second, but we're going to have to pay careful attention to that later on. So for the first part of the question, fewer than 4, what I've actually done is again been really prescriptive with this, and I've drawn out all of the possible values because it's a discrete distribution. We could detect 0, 1, 2, 3, 4, 5, 6 and so on particles rather being detected. We want fewer than 4, so I've ticked the values here that are fewer than 4. So what we're actually looking for is that alpha is less than or equal to 3. This is something that can be done on the calculator, and I'm going to go to the option function and to stat, to distribution. I'm going to go to the Poisson distribution, which is the first one. I'm going to go to PCD because I want the cumulative function, and I'm going to enter in the value that I want, which is 3, and I'm going to enter the parameter value for alpha, which is 3.4. Close the bracket and I press equals, and the answer that I get there to 3 significant figures is 0.558. That concludes the first part of the question. I'm now going to move on to the second part of the question, which asks me for, during a particular period of 5 seconds, more than 10 particles but fewer than 20 beta particles are detected. Now there are 2 things to note here with this next part of the question. I'm actually now dealing with beta, which is the second distribution. Beta is distributed with a mean of 2.6, but the time scale has changed here from 1 second to 5 seconds. So accordingly, I've changed my mean here. If I would expect 2.6 in 1 second, I would expect 13 in 5 seconds. I'm asked here for more than 10, but fewer than 20. And what I do is I then tick the values that satisfy that criteria. So more than 10 is 11, 12, 13, 14, but we want fewer than 20, so we go up to 19. So what we're actually going to ask the calculator to do is to give us 19 or fewer, and then we're going to take away 10 or fewer. I would recommend actually writing that down on your page, so x is less than or equal to 19, minus the probability that x is less than or equal to 10, and then I'm going to go to the buttons and ask the calculator for help. So I'm going to enter here, again it's going to be PCD, it's going to be 19, 13, which is my parameter, minus PCD again, this time it's going to be 10, for the less than or equal to 10, 13, and the value that I get for that is 0.706 to 3 significant figures. And that concludes A part 2. For 2 part B, it asked me to find the probability that during a particular second at least 1 gamma ray is detected. So the gamma rays, if I go back to where I summarised the distribution at the start, are Poisson distributed with 4. And what I'm actually after here, and again I've just summarised this from before, if I'm actually asked for at least 1, that means 1 or more. So it's all of these values up here. I'm going to get that by doing 1 minus the probability that x is actually equal to 0. And at this stage on the calculator, whether or not you choose PPD or PCD is irrelevant, because the PPD value just gives the exactly equal to. Well, the cumulative distribution function there, if you were to choose 0, is only going to give the value for 0 anyway. So I'm going to enter 1 minus PPD 0, comma 4, and if I execute that, the value that I get is 0.982, and that's my final answer. And again, maybe I should have done this before you choose to double underline to make your marks clear for the examiner. B part 2 says during a particular period of 3 seconds gamma rays will be detected in exactly 2 of the 3 seconds. This is a really interesting question actually. It would be all too easy to consider that what you do here is just multiply the Poisson mean for 1 second by 3, but actually it's asking that gamma rays will be detected in exactly 2 of the 3 seconds, and this is a probability question. So from the question before, we've actually got this probability, which was the probability that gamma rays, at least one gamma ray is going to be detected at least once. What I'm going to do then, it means that we're going to have a gamma ray detected, a gamma ray detected, and then a gamma ray not detected. The probability for that would be 0.982 multiplied by 0.982 multiplied by 1 minus 0.982. I'll just carry out that calculation quickly. So 0.982 times 0.982 times, in brackets, 1 minus 0.982, and that equals 0.01736. However, there are 3 ways in which I could achieve that. It could be detected, detected, not detected, or detected, not detected, detected, or not detected, detected, detected. So there are 3 combinations. So I'm going to multiply my previous answer by 3. Note that I didn't cancel my screen, so that I can actually just do 3 times the answer that I had before, and the answer there is 0.0521, and that concludes that part of the question. In the next part, question C, it says the total number of alpha particles, beta particles and gamma rays detected during a period of 10 seconds is modelled by a random variable x. State values for the mean and the standard deviation of x. And this again is a question that I've prepared. In 1 second, what I've simply done here is added up the parameters for each of the alpha, beta and gamma separately, and that came to 10. But we were asked for 10 seconds. That would then be Poisson distributed with a mean of 100. Now for the Poisson distribution, both the mean and the variance are the same. So the mean there would be 100, the variance also would be 100, so the standard deviation is the square root of 100 and is 10. For the final question, part D, it says, this is just a description question right at the end. It's discovered that one of the constituents of the rock can emit a beta particle followed within a second by an alpha particle. Explain why this would make your answer to part C invalid. Well, one of our assumptions that we make for the Poisson distribution is that results and the distributions are independent. Clearly, if that were the case, then we can no longer assume independence. So one of our fundamental criteria for the Poisson distribution is compromised there.